Good evening. We're going to take a look tonight at Chapter 3, Facilities Planning, and go over some things. If you've read Chapter 3, you'll note that there's a whole lot of information there. And let's face it, there's a whole lot of planning that has to take place in order for us to be able to get the most out of our lab facilities. And so we're going to look at the high points of Chapter 3 in this particular PowerPoint. Now, let's face it, chances are you and I could really spend some money to modernize our labs. If you took a look at the Moodle site, you'll note that I've already kind of started the PowerPoint from the assignment on Chapter 2. I have my lab there for you to take a look at. And from those 4 photos, I think you're going to see that mine is pretty much about as good as it's going to get right now. We underwent a project to modernize my lab over a 2-year period, utilizing these all-in-one type computers. And so we got some good deals on them. And at one time I had the monitors, keyboards, mice, and the CPUs all on the table. Wasn't a whole lot of space to be able to spread out and do some work. And so that's what we did. And it cost us about, $12,000–$15,000 to get it done over a 2-year period. But no, first thing we had to do was to kind of do a sort of a preliminary assessment of where we were. Kind of took stock of my PCs. I had about 3 different brands that were sitting in there. All types of different monitors. I pretty much got everybody's leftovers. When they upgraded, I got what was left. And so I looked at the software that I was running, the internet speeds that I would need to be able to run that software without having any problems. And once that was done, it was just a matter of finding what it would work for the budget that we had. And I did not go through a formal improvement plan request. I just went through my dean. She approved my ideas and our IT guys' ideas, and we went from there. In your particular organization, you may have to go through a formal improvement plan request to fill out the paperwork, move that up the chain of command so that you can have the funds allocated to you in order to improve your labs. And so every district, every technical college is a little different, and so just know what the plan is and follow it. Now, your book talks about the types of learning that take place in our labs. And we've got all kinds of learning going on. The first one is reaction learning. Students react to the teacher. They'll listen, observe, and take notes over what's being said. That sounds like much like a very traditional classroom, that you have a bunch of desks in there, the teacher's up on it in the front of the room, on the blackboard or over a projector or smartboard, and they're covering information in the course. Well, that's one type of learning that we can also do in the lab. The second type, interaction learning. Students participate as speakers and listeners. We got two-way communication between the teacher and the students. Teacher is teaching. putting forth information out there for the students. Students are listening to it, taking it in, and then asking questions back to the teacher. Teacher answers the questions and maybe poses some other questions. The students answer that question, and it's always back and forth, back and forth, back and forth. Information is being shared all the time. And so that is a wonderful type of learning right there, especially at a technical college level in a lab class like, say, auto mechanics, where the teacher demonstrates, let's say, how to grind valves. Well, the students see it done, then ask questions. Why did you do it this way? Why this? Why that? Then that just gives the teacher an opportunity to go out and tell them why, and then show them so maybe some things that aren't in a textbook, but come from experience, so that they can gather that and become more skillful. And then last but not least, what usually takes place in our labs, action learning. And that's done by student lab exercises or activities where they're out there using the equipment, building, creating things, and learning by doing. It's a wonderful thing to see whenever that works all together, that students are out there engaged and helping each other, really tapping into that teacher's experience to do a much better job than what they might do otherwise. And so those are the three types of learning that can take place in our labs at any given day and any given time. But let's get down to reality. You and I don't have money trees growing in the back of our schools, that you and I can just go out there and find money to make all kinds of improvements, or to buy the stuff that we need, or to get the equipment that we need, or supplies. And so architects, school systems, school administrators, teachers have come up with a number of models to kind of make the most use out of any kind of lab environment. And there are a number of them. The first, the magnet model. Different disciplines share equipment, physical space, and learning experiences around their common features. So let's say I've got a drafting lab, got 20 computers. Why can't that drafting lab be used when I don't teach class for a, let's say, keyboarding class or a Word class? The equipment's going to be the same. And if I'm not using the room at a certain time of the day, why go out there and spend the money whenever, and build a separate classroom whenever we could share the two? And so there's common features amongst them. The spin-off model expands existing facilities to accommodate additional programs. When we can do that's wonderful. When we can float bonds out there to pay millions of dollars to build buildings and add on to existing facilities, that's a wonderful thing. But right now, money's tight. That may not be viable, but we can do that. We want to expand programs. We can, get T buildings. We could maybe modify existing labs, or we can just expand and build more and more and more around us. Then finally, you got the hybrid spin-off magnet model. It provides facilities for new programs while drawing elements from several existing ones. And involves basically looking at what you've got, seeing what cannot be shared, and then building only what you need. It's a little more conservative model than the spin-off model, which would assume you have the money that you need to get it done from the ground floor on. We can also looking at our various disciplines and seeing if we can cluster them together. Let's say, for example, the machine shop programs and maybe welding programs. Let's say they could maybe share some equipment like cutting saws, maybe some lathes. The welders could use a lathe there to help dress up their pipe. That would be one way that you could have two separate clusters utilizing similar equipment. And then an integrated facility is basically the building around what it is you're trying to do. Starting off and saying, this is the facility that I want to support all of these other programs that I'm trying to start. Would it be some lab that would accommodate, let's say, diesel mechanics, auto mechanics, small engines? What would be the stuff that you could share, even though all three of these programs are going on simultaneously? But yet you have a common core, and all those labs are integrated amongst themselves. So those are the models that are out there. Now, obviously, we got to always deal with space. We never have enough space. It's always trying to find some compromise for space. But how do we determine it? Space management is defined as a science of managing people, time, and money to facilitate change in facilities. Normally we have companies that specialize in that we can call in to do some analysis of what we have, and then make projections saying this is what needs to be done, this is how much it'll cost us, and things like that. But we need to know how much space do we need around the basic station areas where the students are going to be working. Is there enough of a safety zone that passers-by will not be disrupting the person using the equipment, or else any kind of debris or chips or things like that that come off of the machine will not affect anybody else? Then you have support station and ancillary areas. Do you have areas that you need space for like maybe a resource lab, or else for reference material? Let's say in the case of a diesel auto mechanic small engine lab, you're going to need some space to have either computers or a place to store service manuals where the students can go in, grab those service manuals, and then go do the work that they need to do on their vehicle or motor. And those kinds of ancillary areas that are kind of separate there. I think you could probably fit in an instructor's office into that. Obviously, an instructor needs space to hold his or her files, have a place of privacy, and hopefully be a little bit cleaner than maybe the shop area, where they can get away and then either counsel or deal with students one-on-one, and then also get your administrative work done, separate from all of the things that are going on in the lab. Traffic lanes. Those traffic lanes should be well defined and painted off so that people know where to go. Storage areas. Where are you going to store your supplies? Where are you going to store student projects in a safe and secure manner? That takes space. I remember in the shop management class that I had there at LSU years ago, we discussed that you ought to at least look at about a third of the building or the lab's square footage as being a possibility for storage. You just need that much. And then you may need to allow some space for assembly or fabrication space. If you're teaching welding, how much space do you have out there for students to stretch out and start building things? Obviously, if you have 15, 20 students, they can take up a whole lot of room. If you don't have room for that, then you may have to rotate teams or individual students on so many days, so everything isn't all cluttered up and people are running into each other, and then you're getting all the conflicts because, oh, this is my space. No, that's my space. Students get to be very territorial of their areas. And then finally, laboratory instructional resources. Do you have a computer lab? Do you have a library? Or do you have a combination of both? Is there some place where you can get students over there in that area to do that kind of thing? So all of these things are great. All of these things take space. And many times all we've got is just a finite area that we can deal with. Now, what kind of building subsystems are out there for us? Well, your author kind of groups them into four basic areas. Structural. What is the building made out of? What are the walls, the joists, all the physical building that gets supported? What's it all made of? Might be cinder block, might be metal. There are all kinds of building materials that we can use. But that is one subsystem of the lab. Then we got to deal with the ceiling and lighting. Obviously, we need light to be able to do work in a lab, either during the day or at night. And that ceiling, is it closed? Is it open? We're going to have all kinds of dust, all kinds of particulates that are going to be getting out into the air that need to be removed. Well, you've got a gigantic surface area of Celotex or some kind of sealing material that's going to be there, that's going to just absorb that and basically give you a very bad environment for your students to be able to breathe and to work, as well as yourself. And so we got to be concerned about it. And then we got the third component that kind of pulls in three separate components: heating, ventilating, and air conditioning, or our HVAC system. We got to be able to heat an area whenever it's cold. We've got to be able to air condition it, especially down here when it gets hot. And then we need some form of ventilation. We've got to be able to move that air through that building. Our machine shop about 2 years ago was finally able to get air conditioned. We did some work and found some money to do some modifications to the ceiling area of that shop. During the summer, whenever we would run programs, it was nothing for that shop to get up into 110, 112 degrees in the afternoons when the sun was facing the west, which was the way that that shop was facing. I mean, we had fans that were moving air like crazy through that lab, but yet all it was moving was hot air. And so those students suffered. Now, of course, they could definitely go to work in machine shops that were in the same situation, maybe worse. But we made a commitment to do exactly what we needed to do to get air conditioning in there so that we could get our students to be able to learn and learn better. You're not going to learn whenever you're trying to fight heat like that. And so now that we have, it's been a totally different environment out there for our students to learn. They're really doing a whole lot better. And then how are you going to divide up your interior? How are you going to set your machines, divide up your classroom, lecture, demonstration areas, resources, etc.? And so you need to have some kind of plan in place, or some kind of, if nothing else, an idea in place of how those things are going to be spaced out. Getting into some laboratory planning. If you're lucky enough to be on the ground floor, let's say a school or a program that is going to build from the ground up, that is a wonderful kind of situation to be in, because you can offer your input into the design process whenever you meet with the architects and all of the and the contractor and everybody else that's involved in the building of a brand spanking new facility. But most of us got to work with what we've got. But yet, if it ever would happen to you, these would be some things that you would really want to look at to start from day one to plan for the final product. And that would be looking at your work zones. How are you going to lay out that lab so that students are working and not working on top of each other? And of course, the multi-purpose resource zone, where you may have class space, you may have resource space. How will all that integrate together? Storage zone, where you're going to put all the supplies and student projects. And of course, we talked about the ancillary areas. Are you going to have a place for them to wash their hands, to kind of clean up? When I was at the Morgan Smith campus years ago, going to school to be a auto mechanic, we had a locker area where we would come in the morning, change into basically work clothes, work all day in the shop, and then change back into our street clothes at the end of the day. And of course, restroom facilities. Are you going to plan for restroom facilities there in your facility or not? And those are very, very important. Instructor's office. Where will you have to be able to get away from everything and get your work done? Then we look at the ceilings, windows, partitions, and doors. Do you have enough space or a set of double doors, or maybe an overhead door, to be able to get equipment in and out? What about your windows? You don't want them at residential levels, because all kinds of things can hit them. Your book kind of gives a minimum of 9 feet to the base of the window. So like that, they're above you, not at eye level. And of course, what kind of seating are you going to use? Celotex, suspended, maybe blown in, maybe none at all. There are all ramifications that you have to deal with, no matter what kind of sealing treatment that you use. What about the acoustics? Are you going to have material in your wall that does nothing but bounce sound waves back and forth, and it sounds like you're in the middle of a rock concert? Or are you going to build some with using some type of acoustic material that will absorb the sound? And let's face it, you also have other classrooms down the away from you that are going to have to deal with the noise that an activity that's going to take place there in that lab. What about the colors? There are some studies that deal with the types of colors to use. One color has a calming effect. Another color has a aggravating effect on people. The choice is critical. You wouldn't think it might be, but it is. The illumination. We got to have light to work. The major concern about illumination is strobing with fluorescent lights in many labs, especially the woodworking lab, with various pieces of equipment all tied into the same circuit. If that light's blinking at 60 times per second and that blade is also getting turned at 60 cycles per second, there can be a situation where it looks like that blade is standing still if you can't hear the motor running. And I have heard horror stories of students and teachers getting their hands cut off because they thought the blade was still, but yet it was turning because of the strobe effect. And if you aren't sure what that is, very simple thing for you to do. Take a oscillating fan and put it in front of your TV and stand behind it and watch the blades and see if they don't look like they're standing still. So you got to be very, very careful. The way to get around that is to put the lighting and equipment on separate circuits so they're out of phase. Then your thermal environment. How are you going to get rid of heat if you're going to generate it? How are you going to get rid of the cold to heat it? People need to be comfortable in order to work. And so all of those things have to go into your planning. There's some architectural notes that probably your architect are going to kind of, and others are going to look at. The location relationship. How is your lab located in with respect to the rest of the school? As a general rule of thumb, a lot of vocational labs were always away from the school, basically because of the sound, not disturbing other classrooms. With more and better sound suppressing building materials, now they're becoming to be more of an integral part of the building. Climate control data. What's the mean temperature of where you're building that lab? That gives you some idea of how much you're going to need to heat or to cool that facility. Acoustical recommendations for the different types of labs that you're using. Illumination again, storage. Utilities consideration. How much electrical power are you going to need? the absolute worst thing that could happen to you or to me in planning a new facility is where the thing is built, the electricity is hooked up, and you turn everything on, and then the breakers start flipping. And find out that the electrical bus can't carry the current that's needed. It's much, much better to overestimate than underestimate, because once it's done, it's done. So know what kind of electrical draw that lab is going to have under peak conditions. And the data is out there. Architects can get a hold of that very, very easily. The sanitation requirements, getting back to the comment before about bathrooms, and of course handicap accessibility for those bathrooms and wash areas. The surface types. How are we going to finish the floor? How are we going to finish the walls? All those surfaces. Obviously, we want something that's going to clean very easily and won't get damaged over the course of time. And so architects have a wide range of materials that they can choose now, both natural and synthetic, that can get the job done. But obviously, there's a difference in cost. And finally, your door considerations. Where you're going to put your entrance, exit, and emergency doors, providing access out of the lab in case of a fire or some kind of accident or whatever. Where do you put them? How many? You need to go there. What size? And also, how are you going to secure them? Because let's face it, we live in a day and age where people aren't afraid to go out there and steal. So all of those door considerations have to go in the planning. So that ends our little discussion on chapter 3. I guess we'll go ahead and end the lecture at this point, and I will have your assignment posted shortly.